Well, hi everybody. It's a great honor for us to open such a representative conference, and we'll try to enjoy with our talk. Me, Alexey Bataev, and my colleague Zinovy Niz will give you a status update and future directions of OpenMP support in Clang LLVM. Our talk will be separated into parts. At first, I'll give you some introduction into OpenMP, what it is. Then we'll talk about current status of OpenMP support in Clang and LLVM. Also, we discuss runtime library, which became a part of LLVM. Also, we'll talk about support of new feature which was introduced in latest OpenMP 4.0. It's support for heterogeneous programming. And then Zinovy will present you a new feature from OpenMP 4.0. It's support of SIMD constructs with explicit vectorization. So, what is OpenMP? OpenMP is a set of directives, library functions, and environment variables for explicit vectorization, thread level parallelism, and heterogeneous programming. You can use simple constructs like simple pragmas in C, C++ to command your compiler to run some code in parallel. This standard is being developed for 20 years and has several milestones. First versions were focused on thread level loop parallelism. Versions 3.0, 3.1 introduced tasking support, and the latest one, the newest version 4.0, added support for explicit vectorization with SIMD constructs, right? Heterogeneous programming with coprocessors and accelerators. And also added several new features like user-defined reductions, thread affinity support, tasking dependency, and several other features. This standard is very important in high-performance computing, but also several popular packages, several popular software tools use this extension. Maybe we can say that to get the best performance, like image graphics, lame MP3 encoder, and some other tools. As I said, to use the power of OpenMP, you have just mark your code with some simple directives with maybe clauses. But also, you need a compiler which understands these directives, these pragmas, and can translate them into optimized code. Unfortunately, Clang LLVM still doesn't support any version of OpenMP. There is no support at all. This problem was discussed on several conferences, workshops, and there is a group of people from different companies who decided to push OpenMP in Clang LLVM. So we decided to organize a team, so-called team, OpenMP in Clang LLVM, right? Which consists of representatives from several companies like AMD, Argonne National Lab, IBM, Intel, Micron, Texas Instruments, and the University of Houston. Also, this team, there are several members from OpenMP architecture board, which help us with proper OpenMP implementation in Clang LLVM. And we work hard to support OpenMP in Clang LLVM. In this team, we're discussing different problems with support of OpenMP, like reviewing of newly committed or prepared patches with OpenMP, testing support for runtime library, support with library for heterogeneous programming introduced in OpenMP 4.0, and many, many other problems. So, how we implementing OpenMP in Clang LLVM? We're using so-called early outlining in our implementation of OpenMP. This is a very well-known problem in OpenMP in support of different languages, in different compilers. Many other popular compilers use late outlining done in backend. We're using early outlining in frontend. We did it because we don't want to introduce some extension, to add some extension to LLVM, IR, to add some intrinsics. So that's why we decided to use early outlining. Pragmas are represented as regularized AST nodes. There are two kinds of pragmas, actually, executable pragmas and declarative pragmas. So executable pragmas are represented as statements, and declarative pragmas are represented as declarations. Code gen to LLVM IR from AST to LLVM IR follows just standard rules for declarations and statements. And the code for support of runtime library is separated in separate class. So we hope that our code gen is quite is very sorry, I just forget the words, some in English. Is not so target specific. Yeah, do we target API from libIMP5 runtime library, which is actually currently an LLVM runtime library. It was open sourced by Intel, and now it's part of LLVM. And as I said, we're targeting its native API. But CodeGen actually doesn't depend on this API. We can add support for different API. It's not a problem. Here is a common representation of OpenMP constructs in Clang. You can see here an example of representation of OMP parallel directive. It has basic class OMP executable directive, which is basic for all executable directives. And this class has several associated OMP clauses and statement associated with directives. OMP clauses also are represented as classes with one basic class OMP clause, which has several members in accordance to their representation in standard. What is current status of OpenMP support in Clang LLVM? Latest 3.5 release includes parsing and semantic analysis for almost all directives from OpenMP 3.1, except for a couple directives. Also, it includes basic CodeGen support for parallel directive and OMP SIMD constructs. And also, I have to say that this is the very first release which includes runtime library, binaries with OpenMP runtime library. In Clang, we completed support for parsing and SEM of OpenMP 3.1, and added support for several directives from 4.0, like target directive, teams directives, and others. Also, we added code gen for several directives and clauses, like critical directives, if clause, num threads clause, and other clauses. We plan to implement full support for OpenMP 3.1 in upcoming 3.6 release, and implement most of the features from OpenMP 4.0 in version 3.7. But unfortunately, we can't make any promises because we depend on speed of code review. We have a lot of problems with this, actually. Yeah. This is the very, very important problem for us. It's the main obstacle for OpenMP support in Clang. So please pay your attention to our patches. Also, we have some unofficial repository with OpenMP support, which on GitHub. In this repository, we have Clang based on latest 3.5 release, right? With full support of OpenMP 3.1. Also, it supports many features from 4.0 except for target, for offloading, for full support for directives, which allows you to use heterogeneous programming with coprocessors and some accelerators. Also, we have trunk-based branches that maintained by Hal Finkel from Argonne National Lab. So you can try this implementation to see the benefits of OpenMP, to see how it works with your code, absolutely for free. Here is a summary of current status of OpenMP support in Clang. As you can see, in trunk, we have support, as I said, only for parsing and semi-analysis for pragmas from OpenMP 3.1, like parallel pragmas, work sharing pragmas, tasking pragmas, and other features from OpenMP 3.1. In trunk, in our unofficial branch, we have full support for OpenMP 3.1, and we have support for almost all features from OpenMP 4.0 except for offloading. Another important thing in OpenMP support in Clang LLVM is runtime library. As I said, this runtime library was open sourced by Intel, and now it's part of LLVM. This runtime library works on many platforms, on many OSs. We tested it. It can be built by many compilers, but there are several problems still with this runtime library which should be solved, like testing support. Currently, we're working hard to add testing support for this runtime library, and previously mentioned OpenMP in Clang LLVM team works on this problem, and we're trying to adapt OpenUH test suite for these purposes with the help of Sunita Chandrasekaran from University of Houston. Thank you, Sunita. Another important feature of latest OpenMP 4.0 is offloading, is support for offloading and support for heterogeneous programming with coprocessor accelerators. To support this feature, you need an additional library, except for runtime library for LLVM. For OpenMP, you need an additional library for offloading support. Currently, this runtime library is actively developed by several engineers from IBM, Texas Instruments, and Intel. And we're discussing the problems with this runtime library development in also previously mentioned OpenMP and Clang team. How are we going to implement this feature? We generate a special executable called fat binary, which includes code and data for target, for a host, and all targets which should be used for offloading. Then, using provided interfaces with libomp target library, this code and data are loaded into accelerators or GPUs or coprocessors, which execute their parts of the code and then load the results back to host, again using this new runtime library. This is not implemented yet. We're working on this feature also. The parsing and SEMA, of course, for these directives also ready, and you can try it in our unofficial repository. We started adding code gen for offloading support, and Samuel Amtau from IBM added several patches with support of code gen for this feature in our unofficial repository. Latest standards of OpenMP, OpenMP 4.0, added another new feature called explicit vectorization with SIMD construct. And my colleague Zinovy Nis will give you an update about this feature, what is implemented, what should be implemented. Now it's your move, Chief.
Thanks. Hi, everybody. I'd like to talk about a brand new feature in our latest OMP standard. It's a CMD feature support. OK, let's start from the beginning. CMD, what is it? Imagine a typical computational program which takes a sequence or stream of input data, crunches them with a stream of instructions, and produces a result, also stream of data. What if you want to run this program faster? Of course, in the modern approach to this is to parallelize your program to utilize all the cores of your CPUs. So you just run your program on all the cores and get a performance there. So this can be achieved easily by using, for example, fork in Unix or P threads in POSIX or begin threadx in Windows, or by using explicit parallelization with pragmas like pragma-OMP for parallel 4. This kind of parallelization is called thread-level parallelism. But there is another option to get a performance. We can handle the data simultaneously. It means that we have to use special instructions. They are called CMD or vector instructions that handle not a scalar chunks of data, but they take a whole vector of data, handle it, and produce also vector result. For example, the simplest example is vector addition. You feed your vector addition instruction with two vectors, and it produces a new vector which has a sum of two corresponding elements in its resulting elements. Rather simple. This kind of Parallelism is called data level parallelism, or CMD, single instruction, multiple data, or vector instruction, if you like. There are also a lot of ways to get vector instruction emitted in your code. For example, after vectorization in most of modern compilers, including LLVM, or you may manually write intrinsics or assembler code, and so on. And also, of course, you can use pragma-OMP CMD, a brand new feature in the latest standard. The profit with vector instruction is related to the fact that vector instruction works faster than a sequence of scalar instruction doing the same. For example, one vector instruction can add, for example, 4 float elements at much faster than you add these floats in a scalar sequence of instructions. So here is the performance. And the more vector width, the more data you handle at a time. So you can see the chart, and vector width constantly evolves, and now it's 512 for modern Intel architectures, for example. Please note that first and second options are rather independent. So in the first case, you load as many cores as you have in your CPU. And in the second case, you load a single core, but you load it as much as possible. So why not to do both? We can mix these approaches and get the highest performance available for your platform. I don't know other nice ways, but for me, the simplest way is to use a combined pragma, OMP, parallel 4, and CMD. Okay, and at this point, you should feel yourself like a maniac with a brand new chainsaw. So how can we get a new CMD instruction? Okay, imagine we work hard for many months and got this sophisticated program. It's a very hot loop, and your boss wants you to make it much more faster. And it's reasonable. Okay, of course, you should start from the simplest way. The simplest way is, of course, to use an autovectorizer embedded in your compiler. In case of LLVM or Clang, we implicitly enable autovectorization since optimization level 2, 3, fast, speed, or maybe some other. So you absolutely free get high and transparent portability. So if you need to retarget your code for any other platform, you just recompile it. High and transparent scalability. If other target has a wider vector, it's not your problem. It's problem of your compiler. No development cost at all. Your code is not changed at all. All you need is just a few switches or single switch in command line. But you get and pay for it by unpredictable performance. Unpredictable means that a hot loop in your program may not be auto-vectorized for some reasons. It depends on your autovectorizer. So imagine the worst. Our loop was not auto-vectorized. What else can we do? Of course, we can do it manually. Here we use intrinsics. We may use also inline assembler or, I don't know, machine codes encoded, but I decided to use intrinsics. It's, as you can see, it has a very low portability. These intrinsics are Intel architecture specific, and even more, these intrinsics work best on some specific Intel architectures. For newer architectures, you should use some other intrinsics. So portability is not good here, but you get a maximum available performance here. It's a good news. Also, we have a high development cost here because not everybody can just sit and write this intrinsic. You at least need to read some manuals and, I don't know, The scalability is also not so good. Vector width is hardly encoded here. So, as you can see, there is a free space. It's not just a free space, it's a free space for explicit vectorization. By using explicit vectorization, you tell your compiler that you need a particular given loop to be forcibly vectorized. So, compiler should do his best to vectorize this loop by skipping some checks and so on. And it seems that it's one of the best choices because you get a high transparent portability. You just recompile the code for new target, like in case of Autovectorization. Scalability is also the same as in case of Autovectorization. And you get a predictable performance in that sense that you are almost have a guarantee that the desired loop, hot loop, will be vectorized. Okay, and on the next slide, we will discuss a bit why we can always rely on Autovectorizer, why it may fail. In case of LLVM, vectorizer may fail in a few different cases. The first one, most popular, is cause heuristic says no, because before performing the vectorization, Autovectorizers tries to estimate the cost of new generating vector version of your loop. It may be very high to some reasons, and Autovectorizer decided not to vectorize because it's useless. It's too expensive compared to origin scalar code. Another case is non-trivial data dependencies. In the sample, in the right, we have k and n values which are unknown and compile time. The scope here is very small, and compiler have no idea what values n and k can have. So it will also fail to vectorize this loop. Third option is overhead is too high for runtime checks. As you see, there are 5 pointers to arrays in this sample, and if pointer to A is aliased or overlapped for some I and key values with B, C, D, or E, loop must not be vectorized, or it leads to incorrect code with changed semantics compared to the source semantics. And the last but not the least, loop will not be vectorized, in LLVM at least, if this loop is not the innermost. In this case, we have a nest of 2 loops, and only the last loop will be vectorized. So if we compile with trunk LLVM, we get can't vectorize due to memory conflicts. Okay. But by using OpenMP CMD pragmas, we can vectorize even this code. In the sample in the lower left, we can see pragma-OMP CMD collapse. Collapse allows you to collapse a nest of loops into a flat iteration space. And so we have a new loop, one loop. And this loop can be vectorized by Autovectorization built into LLVM, for example.
This is what we have in trunk.
Yeah, it's what we have in trunk right now. You might try the sample. Okay, so the log says that we can vectorize this loop. Good news. And now a few words about status. OMP CMD pragmas mostly work. Some exotic clauses still do not work. But we are working on it to enable all the features introduced by new OpenMP CMD standard. And the sample here shows how we present OpenMP CMD pragmas in LLVM IR. They are represented by metadata. So you can see loop vectorizer enable true and loop vectorizer with for representing a safe len clause. In the backend, OpenMP CMD pragmas must be supported by Autovectorizer itself. It already recognizes the metadata and forces vectorization for loops marked with this metadata. Collapse, safe len, and align clauses of pragma-OMP CMD can be used right now. Other clauses are under development, as I said. We have some issues in the backend, but we are working with community to overcome them and to fix them soon. So I hope for the best. So to put a summary, we would like to have your feedback on these new features. We're working actively on enabling them. And if you face with any issues, any problems, please let us know. We will fix it as soon as possible. Hope you will like these new features. Thank you very much for your attention. And if you have questions,
sorry. We have time for questions, 5 or 10 minutes. If you have a question, raise your hand. I'll try to bring you the microphone.
Have you considered supporting Android, x86, of course?
OMP CMD features of OpenMP is not related to particular architecture. It's platform independent. So we also support ARM, MIPS, Intel, and any other architecture operating system.
Yes, right.
So yes, we support.
Hi, so I believe Silk Plus has a similar feature to OpenMP SIMD. So how do you see those interacting?
Well, actually, we are going to commit support for pure SIMD construct without OMP, right? Which is part of Silk Plus, so it will be supported, I hope, very soon.
How generic is your early outliner? Because it could be used in some other languages, such as C++, or OpenCL, curl, and so on.
There is a class captured statement called captured statement. It can capture variables and can generate outline function. I proposed to read Kleckner to use it for support of Windows exception handling. So you can also use it, of course. There are simple examples in the code. It has support for simple pragma like Clang capture. You can see an example of implementation of this feature and how to use it.
With the future plans for number pragma target, if you have CPU, GPU, Xeon Phi, is the programmer deciding what the target will be in all cases, or are there opportunities for load balancing?
Sorry, could you repeat, please, your question?
Is the programmer hard coding a specific target?
No. He has not to hard code some specific target. It is supported automatically by some options.
In the example that you showed with the doubly nested loops, the auto said that it failed because it couldn't tell if there was aliasing. And then you add the pragma, and suddenly that looks like it went away. Does that mean that the pragma implies something about the aliasing?
Yes.
Yeah.
It adds some metadata to generate the LLVM IR, which tells vectorizer to ignore.
When autovectorizers see this metadata associated with the given loop, LLVM.loop.vectorize.enable set to true, it skips some memory checks, profitability checks, and tries to vectorize the loop.
Hi. So if you refer to your double-nested example, you got a unknown value k here. So how would that the SIMD pragma helps you to generate code for unknown stride?
In fact, pragma OpenMP CMD allows you to vectorize your code, but it's not guaranteed to be safe or reasonable or profitable. So it's a case that it's an explicit vectorization. So when you mark your code with this pragma, you know that it's profitable and it is safe. Because for compiler, because for compiler, it's rather hard in many cases to know that it is safe to vectorize, that there is no dependencies between iterations and so on. So by using pragmas, you give a hint to your compiler. Compiler, it is safe and it's profitable. I know it, so please just vectorize, don't ask me anything.
Yes, you have to be sure that your code can be vectorized.
And to be honest, the generated code here, vectorized code, is like a spaghetti code. It's very huge, and I'm not sure it's very efficient. It's just a sample. But for many applications, this pragma really helps. We have a lot of benchmarks for this. Yeah.
Right. For your to-do, the first item is to handle the problem caused by the metadata. Front end is used to pass the information for vectorization to very late. So did you make some problem like some optimization will break that metadata so that vectorization cannot happen? And how are you going to handle that?
Yeah, we have an issue with metadata lost when they are propagated through different passes. And we also have some talks in the community. In some cases, it was fixed. For example, for loop rotation pass, it was fixed a few months ago. And now we faced with some other passes with the same issue. And we are working on a more general solution, not to fix each pass, but to make some more general solution. So yes, that's a problem, and it's nice you mentioned it.
So for your test case over there, so if the compiler discovers that it's not safe to vectorize, like for example you do a width of 4, but the compiler knows that it's not legal, so will you vectorize?
No, but the compiler will not vectorize in the cases when it's proven that it's not safe. But in fact, we can add some knobs to control it. I'm not sure it makes sense, but we can.
This work is not completed yet, so
yeah.
Hi. So with your features for SIMD and additional parallelism, it appears to me that you can express parallelism really well. So are you proposing this will you be proposing OpenMP as an alternative to other SIMD languages like OpenCL?
I don't think that OpenMP CMD will be the only solution for CMD vectorization, so they can coexist. I don't see any problems here, if I understand your question.
There. I would follow up briefly on the question about drop metadata. It sounds like you have concrete examples of cases where metadata is being dropped. Is there an easy way to find these bugs? Have they been filed? I am also interested in cases where metadata gets dropped, and I am happy to do the work of fixing them if you can point them out to me.
The latest thing I remember, I had issues with lost metadata in global value numbering. With global value numbering, after critical each is splitted, metadata are lost. So I tried to fix it manually, but the solution rather dirty. It was not accepted. So we work on it to make it more general. We can find you can find a discussion in our mailing list, the development mailing list.
If you file an LLVM bug, your odds of getting them fixed go up a lot.
I filed a bug and filed a solution, but I think the solution is not so good yet. It's not general. So we have to fix a lot of passes that can destroy this metadata. It's not good solution. We have something more general, maybe to put metadata on some other place, because in LLVM you don't have a dedicated loop entity. You mark your loop on backward branches. It's not a good idea in many senses. So maybe something must be changed here. I'll be happy if it changes.
Let's go ahead and thank the speakers. And